My name is Gennadii Donchyts. I work for Deltaris, a company called Deltaris. It's a very large Dutch research institute, organization, non-for-profit organization. So we do a lot of projects related to water, actually everything related to water we deal with. And my presentation, I'm Ukrainian, so if there are mistakes in English, then sorry. My presentation goes about GeoAPI and NetTopologySuite SharpMap and using the integrated environmental model application. Can you still read this? I found out that one fact that if you can read this text, it feels very strange. You have all letters mixed up and it's still readable. If you don't look in details on every word. Okay, my presentation today will go about something different. It's about GIS and integrated environmental modeling applications. Actually, integrated, I would write water modeling applications. And first I will talk a bit about libraries we use, SharpMap, and all libraries which come with it. And then I will look on some examples of integrated environmental modeling applications. And then I hope I will have some time left for a short live demo. So about SharpMap. SharpMap is an open source library released under LGPL. But if you use SharpMap, you actually have to use some few other libraries, and one of them is GeoAPI and NetTopologySuite. This diagram shows actually amount of source code you have in this library. So you can see that GeoAPI is actually quite small. It's about 150, 160 kilobyte library with mainly containing interfaces, defining some geometry specification, coordinate reference system, and all these kinds of things. And it's actually implemented by NetTopologySuite, which implements all these geometry types and all kind of geospatial operations, intersections, and so on. It's a NetTopologySuite. It's a port of Java TopologySuite. So it was ported, but with to C#, also, yeah, keeping in mind C# style, using properties and all kind of things. And SharpMap itself, it's a library which is able to render nice maps, so you can add different layers, rasters, vectors, and you can have use different data sources. And yeah, GeoAPI, we hope also that it will be something that we will share between SharpMap and .special communities. And these libraries we use quite a lot, extensively in our software. And our software mainly focused on, I mentioned, integrated environmental modeling application, which means that we want to configure a different type of models, and we run different type of models to simulate different physical processes like rainfall, runoff, and flow of water in river networks, or rainfall and runoffs can be also simulated in different ways using kind of lumped approach. Where you calculate simple weather for the whole catchment, or you can have distributed model where you include also routing of water. And the idea or our end goal is actually to have all this model run in parallel, if necessary, because frequently you have physical processes which are interdependent. So you have to simulate your processes simultaneously, and that's quite a challenge. But we started with this. First, we have a few of these models already running. I will show, just to get a feeling about what kind of data I'm talking about, and then we can project it to GIS applications. This is example of some unstructured grid model, and these are I'm showing the results of the model. I will turn this animation on, and then you can see that it's water flows. This is simulated by something we call unstructured flexible mesh model, and then you can see that grid itself it's unstructured. So it means that you have cells which are rectangular, some are triangular, some many model vertices, and they are also interconnected. So it's simply that's what model uses, and this can be pretty large grids with a lot of cells. You can imagine this result file is about 7 gigabytes. And it works very smoothly with this. It's kind of prototype software, so it's very fast. But I think that's our future is that our GIS systems will have this as a 3D visualization, and the same that it will work interchangeably in our GIS applications. So that's kind of gives me. But imagine that if you integrate this model with like 3 models of this type, and 1D, 2D, 3D, they run in parallel, and you want to visualize them in parallel, maybe they run on different computers. So that's quite a challenge for future integrated environmental modeling. Okay, let's get back to the presentation. Next, about what we built, or what we are building, is the main focus was at the beginning to build a desktop system, a graphical user interface, which will allow to schematize this type of models. Schematize means that you want to create a kind of schematic map, or maybe import from GIS data, rivers, polylines, and all kind of objects, and also information about the relation between these objects, and then you want to configure a specific model with all time-dependent data, run it, visualize, store, exchange, all these kind of tasks. And yeah, if I look on challenges we had during implementation, is challenges related to geospatial libraries. These are 3 bullets. One is time. So if you deal with models, a lot of things are time-dependent, or not time-dependent is more exception actually. So everything is time-dependent, and in GIS world, classically it was not time-dependent, now it becomes more. So in GIS standards, there's not so much time if you look in open source libraries. And the same about features coverages. It's in some libraries they're available, in some not. If you read some specification standards, they are defined in a very abstract way which you cannot understand. But in practical application, you need something simple and workable. And I listed also topology. It means when you have your polylines and polygons, in reality you schematize some part of reality, and they have connections with each other. So if you start moving these objects, you want them to go together with each other. So if you do routing, you want to know information that is in the graph and how they are connected to each other. So these are kind of challenging part. And then also intersection of all of them. So you have data defined on network, but it's also time dependent, and you want to store it in different file formats. All these kind of issues. And another type of issues, I told that our focus was on graphical user interface, but actually we had to deal with different type of users. So when we start building user interface, we realize that some users, they want user interface, but some model developers, they are scientists, they just write modeling software, they work in Fortran, they think in Fortran. So if you tell them about something about aspects and objects and classes, they don't understand it. Or if you tell about problems you're solving, it's also frequently far from reality. And the same is on other side. You get more abstract if programmers start talking about aspects and code median and other things. It's also very, very complicated. And once you start releasing systems, they start asking questions. I want to redo functionality. I want to run macro. Can I do this? I can do it in Excel. How can I do it here? And then you have scripting, then you have backward compatibility of file formats. If you release, they say a lot of projects, they want to open in the new system, and then they don't realize that it's for developers. It's maybe costs 2 times more. Takes 2 times more effort to implement it, and all kind of other things. And of course you have bugs, and to release make stable system is quite a challenge. We ended up with something, some architecture like this on this slide. So we have defined some very minimalistic core API where we define concept of that users work with projects. It doesn't matter if it's console or user interface. You have application. We need to plug in pluggable framework. We need to define some workflow where we run different models for different import-export activities. On top of that, you have API of user interface where you want windows and toolbars and so on. And that's the basis for graphical user interface. And then we added some default plugins to store data in its kind of hybrid store, relational, multidimensional we have one of main components is geospatial components. It's SharpMap and everything around it. And we extended it quite a lot. And then we have some hyper-specific objects like rivers, channels, pipes, cross-sections, wears, all kind of hydrological stuff. And then scripting plugin and some other libraries. And then dynamic part. So this part is something which is continuously improving in quality nowadays. And below it will be able to plug in different model applications like integrate some different models or different visualization techniques or some open MyCompliance. It's a model linking framework or API standard. And that's a way how it can scale or can be applied to different applications. If you remove this part below, it's just some half JS, half data management system. That's what you get. Once you start filling in these plugins, then you get some more specific application, like shown on this slide. This is 1D, is a screenshot of 1D application where rivers are modeled, and you see a lot of cross sections. It was Steve Bo's presentation. He showed on some application of Sobek. So Sobek is something which runs in background with this user interface, and then you can visualize the results on the map and run the stream. And here below a few slides about model called XBeach. It's two-dimensional model, and you can see also profiles near shore, how water flows and some erosion processes, and it's all time dependent and map and time series and so on. And it also works on common line version. Works on we have common line version of system which we made tested. It works under Linux, even under normal. Most of components except some user interface doesn't work quite nicely. And I'm not sure. I did not look on time. I have still okay, 10 moments. So the next part is I will show some examples of live examples of the system. First one is related to XBeach. It's I mentioned that it's kind of near shore hydrodynamic model, which is able to simulate water flow, but also all erosion processes for longer term. And the model itself, it's open source, and we created really very prototype within 5 days with a group of 3 people. We were able to integrate model and make this system called a Delta Shell, so create Delta Shell plugin, which has model wrapper, which is able to exchange data with the model computational kernel. And we also added some tools to visualize data on the map and peer data on the time series. And practical application is related a lot to the next one, to the local area where we have Ministry of Water and Transport, project for Ministry of Water and Transport. And they have a lot of measurements data for last 50 years, how the coast had been changed, and like dynamics of all these profiles. And the idea of the model was to use models to simulate these kind of processes, erosion processes, and use it also to decide in which parts they have to add sand, kind of call it in Dutch, glaciers. I don't know how it's called in English. So I will switch to user interface. So this is how the user interface looks like. And I have model pre-configured, so I will simply import existing model. Here you see a lot of importer. You have different data types. One of them is model. And I will try to use some existing model files to import this model. And you can see that you can then navigate all model input-output data, like bathymetry. This in background, it's a SharpMap, but the model grid, it uses structured curvilinear grid. So it can be, can be curvilinear as well. And you can see bathymetry, you can see all these values, you can look on the click. Oh, I hope not crash. Start computer a few times, so I think I better just stop it. I'm using development version, so it can be unstable, and it has all plugins which we have developed for all time. So it's I will just run it for a little bit and try to show some results. And you can see that there are some variables available, some model output variables available for visualization, for analysis, and it's you can it's animated, it's time dependent. You can see values, you can see maps changing. Places animation. You can say, okay, I'm interested in how the profile of this variable will look like. So you can say, okay, I want to build this section along this polyline, and then yeah, the nice thing is that if you change time, the time this section actually updates. Can create query value for specific selection and show time series, or I can even move this profile and say, okay, I want to see it here. So it's kind of all slicing in different dimensions, and that's how the user is supposed to work with it. And very fast, just show some functionality of working with one-dimensional model. So I will add new flow model from scratch. So nothing is imported. We can import existing river network from GIS files. But if I start editing this water flow model, one-dimensional, I have one of input data is network, and I get map of that network here. I can just schematize, draw it, or import from existing polyline files. It detects topology by itself, so it looks on tolerance, the distance between ends of polylines, and it's able to construct graph from that. Yeah, user is able then to, once I draw it, it knows about topology of this relations between these polylines. And I can draw this, let's call it routes on this network, so I can create one or another. It's used internally, it converts this network to graph and use this open source library called QuickGraph to construct shortest diagram methods. But practically we use it for like visualize data along the selected routes. So delete this, and then I will one more minute try to make this model run. So in order to run, just having a river network is not enough. I need at least some information about cross sections or profiles, so how the river looks like. So I created some default cross section on every of this ridge. And the next step is I need to define where water comes from, because Dutch examples that by default it's closed. We have a lot of channels, but they don't flow anywhere. So that was also a decision, but I guess it should be configurable. Then I can define that this is open boundary, and the result is that I will be able to enter here single value or time series. So let's put 10 cubic meter per second. And then I need something called computational. We have something called validation. So user is able to validate and check what kind of data he's still missing. And it says that you need to define computational grid. So I will put something with, I hope this will work. So it's every 100 meters is computational cell added. And that's it. I will be able to just run the simulation. I hope it will run. Okay. It took some time. I guess it has to do with some licensing. But the result is that you can just visualize this result after run. These are output data. It's something we call network coverage, and you're able to just visualize it along as a time animation, or just select specific location and query time series for selected variables, and then look how this evolution of this looks like. And what I showed before, this routes, you can if you in this.
Did you set elevation? elevation heights of the stream network?
Yeah, it's this cross section. It's now set. It simply used default elevation. But what I wanted to show also is that yeah, if I want to show how it will look like along the stream, then something called side view, and then you can see how water flows along the river. So we can modify cross section and give him different form, different elevation in any location, different roughness. So you have different bottom types. So that all these hydraulic parameters are available. Or add a lot of all hydraulic structures like pumps and gears. So that's everything which is available. So full-scale hydraulic modeling. So that's how it looks like. And I didn't mention. I guess I don't have time. We worked also on something called under-redo functionality, which is now in prototype version. I hope it will not crash. So I can move while I draw a network, I can of course make modifications to it. And the nice thing is that we can track all these changes and we can crash. I guess I had to because I ran model and I did a lot of action, so that's why I did it very smooth. And another thing to mention is that we have something called scripting functionality. So I guess I have to start to finish our presentation. So with scripting functionality, the user is actually able to build his own schematization using Python script. And I think I will make one more click and then I will finish. So I will add here a script, and what it can do is, so I will show example where it's the same. I have a Python script here, and what it does practically, it uses IronPython, and it creates something we call hydro network from scratch. Assigns geometry points, polylines. You can also script importing or run it off model here, and then it adds result to the project. And once I run the script, what happens is it will add this hydro network, and you see that this whole network structure is scripted from the Python script. You can also modify this in data, so it's similar to like QGIS, IronPython, or some other systems. Okay, I guess that's it.